Hi there, guys. So I've got about an hour here in which I'm going to attempt to make the start of an IA project, and a project which could potentially be used for any one of the courses, really. Um, okay, so I've got my cup of tea with me. That's important. Drinking temperature at the moment. I've got a copy of the HLAI Oxford textbook here as well. I was just looking in this. If you're struggling for ideas on investigate possible investigations, then note that at the end of each of the chapters, like for example at the end of chapter 1 here, you have a modelling and investigation activity. So there are loads of investigations in your book which could lead on to be something that you're interested in, or could give you ideas as to how you could go on and also use content from your book as well. So work which is commensurate with the level of your course. Obviously, they follow on from the chapters. So this one, for example, this is just after the first chapter. There's one here which is talking about the three squares problem. Okay, so yeah, lots of things to look through there for some inspiration. Lots of projects end up being data projects, database projects, and they tend to be fairly, perhaps slightly easier to do. It may be that you're trying to do a project where you're collecting, I don't know, say like global data, GDP data, economic data, health data. You might be looking at lots of information for countries. You may be doing some data mining where you're comparing many different factors to each other. You might be interested in regression, in correlation analysis, and potentially regression lines between those things as well. I'm not going to do that here. What I'm going to do is I'm going to look at one bit of information over time. In fact, what I'm going to look at is Moore's law. You can see I just searched this one a second ago. Start this video for the first time. I'll probably mess up again. Right, Moore's law. Okay, so the Moore's law is, now I've seen students do this before. I've seen a few students do this, and in fact, if you know something's been done before, that probably is not going to score particularly highly in terms of personal engagement, because we know that these projects are out there, and of course, all examiners have seen many projects. If I've been teaching, been doing the IA for 5 years or so, and I've come across multiple copies of projects, then of course examiners see many more projects. So I would steer away from anything which is a complete copy of something that you've seen from before, a copy of the idea. But either way, the idea of taking something which grows potentially exponentially over time is what I'm looking at here, and this could be a useful type of project to look into. But what I'm particularly going to show you in this diminishing hour is how to collect the data, how to clean the data, how to save it neatly, how to get a real project chunk of your project over and done with, which could lead on, but either way is a useful hour of your time, hopefully. So you could be choosing, while I'm doing this, you could be thinking about something that you want to clean and data which you collect and clean as well. So as I said, it could be some sort of world statistics. It might be you have a particular interest in, I don't know, football or pandemics or whatever, and you could try and collect some data over time, potentially collect multiple. If you've got an idea about how things relate to each other, then you might want to collect several bits of information, say, for example, per country, if you've got some ideas about how things relate. You kind of want to have an idea as to where you're going before you collect the data, a little bit of an idea at least, because you want to do this all in one go. Going back and collecting some other bit of data is going to take a long time once you've decided later on that you need something else. Okay, well, what is Moore's law? So Moore's law is a prediction made by an American engineer, Gordon Moore, in 1965, that the number of transistors per silicon chip doubles every year. Right, doubling every year. Okay, well, let's just have a look at that. Let's say 2 to the power of 100 years. Well, that's such a big number that that's going to be 1 followed by 30 zeros here ish. I mean, that's such an extraordinarily large number that I'm sure that's more than the grains of sand on the earth. So this is likely to fail at some stage. So I've got a bit of an idea on this. Not stolen, I promise, from those projects which I've seen. Okay, so I've got a bit of an idea as to what's going to happen here. I've got my transistor count on my left-hand axis, and I've got my years along the bottom. I want to go from around 1965. Got to find some decent data too. 2020s, where I've got good data up until, and I'm expecting to see a graph which looks something like this, and then suddenly like that. Okay, because if you think about, if this is the maximum in 2020, if it halves in 2019, then you're here. If it halves again in 2018, then you're here, and so on. So suddenly you're going to get really close to this line here. Now, there are ways of dealing with this to see what's happening here, and one of those ways is linearizing your data. So I'm aware that I could use that in this case as well. So first of all, though, I just want to get my data. I want to get this data, I want to clean this data as well. Okay, in terms of what I might use for this project, what might I use? So I'm doing this completely from scratch. So what might I use? I'm definitely going to use some functions. I know that I should get anything which grows with a constant rate, like for example, stock markets or potentially funds over a long period of time, maybe should grow at, I don't know, 5% a year or something or other. So if you have that kind of idea, we're talking about exponential growth here. So exponential growth, so exponential models, and obviously you can look up for what an exponential function is yourself. I'm probably going to do some regression analysis, which I can do on Excel. Do on my calculator. I can linearize. This is kind of fancy. It's not going to be in all courses, but it's definitely in the HLAI course. I could linearize my y numbers, my y-axis. Okay, and that's basically linearizing a log model. An exponential model by taking logs of both sides. Again, if you want to look into that, you can. What else am I going to do? What else could I do? I could do, in terms of functions, I could do piecewise functions. They turn up a lot. So if you don't know what a piecewise function is, it's just basically saying, we're splitting things up in terms of what's happening in this section, and this section according to the different domains, and then making a different function for each one. Okay, and again, that might be through multiple regression analyses. I could use a logistic model. The logistic model, let's have a little look at this one. So this is quite nice. This is new to the course, or to at least the HLAI course. This logistic model, let's have a little look at this one. So it gives you something which looks like, so instead of just getting exponential growth at the start, let's click on this one here. So instead of just getting exponential growth at the start, it then sort of tails off and sort of hits a limit up here. This is this is a version of a logistic model here, and potentially Excel will allow us to do that as well. Definitely your TI Inspire allows you to do regression analysis for that model as well. So that's a really nice model. And so I've got another idea about this in terms of, I think that my graph might look like that, okay, over time. But I also think it could look like this. And it could like tail off, okay? And potentially in the long run, there may be some physical limit that we reach as well. So I'm interested to know whether or not we're anywhere near to hitting that limit too. So that could be a logistic model instead that I'm looking to create, or potentially it's an exponential model up until a certain point, and then it's another exponential model, maybe an exponential decay model beyond that point. So again, I'm looking at potentially a piecewise function there too. So there's many different directions which I could go in here. I could also be looking at transistors. I could be looking at some other measure of computing power. and see how they relate to each other. So I could be seeing if this law is also true in with, I don't know, another type of metric. And then I could be looking at maybe transformations between those two graphs as well. So there's lots and lots of mathematics which we could use here. Yeah, so that's why I picked on this one to start off with. Yeah, right. Okay, so let's get started on this. I think I spent a fair bit of time on talking about it. Anything else to think about? What else you could use there? Come back to it later. Okay, so let's collect some information. Let's go to good old Wikipedia. Let's see what Wikipedia is saying. Okay. Oh, there we go. There's a graph there, right? With a transistor count over time. It's been done. Of course, it's been done. Okay, but that's interesting. But I want to check it myself. And let me think. Let's just do another. Maybe transistor count is not so good. What are measures of computing power? Performance metrics, or like lots of things here. Power of. I might have to delete this bit. Okay, number of transistors. Okay, maybe there's some other factors. Forecast roadmaps. Okay, now listen, I said I was going to go for this. There may be some other things that you could look at, but I'm basically going to do this, and you're not going to do this anyway. But you can find something similar to look at, and I'm going to show you how this one would work. Obviously, this analysis is done on Wikipedia as well. Okay, so let's see if I can find the number of. Let's see if I can actually find the number of transistors. Okay, number of transistors. It's not going well, is it? Number of transistors. Transistors over time. And record. Transistor count over time and record. Transistor count. There we go. I think that's what I want. Transistor count. Okay, so come on, where's the table? Oh, here's the table. Okay, so here we go. So we've got here transistor count, date of introduction, designer, MOS process. Okay, don't know what that is. Metal oxide semiconductor field effect transistor. The area of the thing there, little units thing there. Okay, so this looks like my table. That looks good. Okay, and then so this is what we're talking about. GPUs as well, right? So there's transistor count for GPUs. I don't know which one to use. This is starting from 1982, so that doesn't go back to 1965. Okay, what else have they got? Field programmable gate array. Introduction in 1997. We're going to have to put all of this together. Memory. I might be interested in memory. RAM memory, flash memory. Which one am I interested in? I'm not sure. Okay, so this starts back in 1963 as well. Okay, so there's RAM memory and flash memory here as well. And then read-only memory. I don't know which one to use. This list includes early transistorized computers, second generation, third generation. Okay, so there's lots of things which I could use. I think I'm going to go with that top list. And what was it? This one was saying this goes from 1970 all the way up to. Oh, here we go. This is good. So this is a fairly good and consistent measure over time. Then it would seem going all the way up to 2020, right? So what I'm going to do is I'm now going to copy and paste all of this, right? Okay, and it's got lots and lots of information here, right? And so this is going to be pretty boring, but I'm going to clean all of this stuff. So all I've done is copied that, and right, so I'm going to go into my next page, and let's start B2, and I'm going to paste this, and I'm going to paste, let's go matching format destination. Let's see what I've got. Yeah, that looks good. Okay, so what I've done there is I've gone to a left click on the mouse, and I've gone to paste by matching the destination format, so matching the Excel file there. Okay, now every time that I'm going to do this, I want to say where I've got this from. So I want to, for my bibliography, let's just note down here that that's my bibliography. That's where this is coming from. The information is coming from in this case. Now this is, in this case, I'm going to name it. This is my raw data. Okay. Now, so if ever I lose anything, or if I've done something and I don't like what I've done, let's put that there at the top. Let's just give that a little space there, so it's insert space there. Right. So this is my raw data. Now what I'm going to do is automatically I'm going to make a copy of this, and I'm going to move it to the end. So I'm now going to start working on this data. Okay, so I don't know, let's call it clean one. Okay, so first of all, there's just way too much data for me to deal with. All that's really necessary in this problem. I really just want the maximum for any 1 year. So what I'm going to do is I'm going to go back to my first year. So my transistor count is here, and also look, I've got all this information here. I've got extra bits of information. I just want the raw number there. Okay, so I'm going to change that transistor count to the raw number and the maximum for any 1 year as well. And there may be other decisions that I'm going to have to make as I go through. And I'm just going to write down really quickly what I'm doing here as well, so that I know when I come back to write this up what was going on too. So like little reflections. So we can start by making our reflections now. So what reflections can we make? Reflections are, I don't care about area. Maybe I should care about area, but no, I don't. Remove area. I'm going to MOS process. I'm going to remove area. I'm going to remove the MOS process as well. I don't care about that. Do I care about the designer? Not really. I don't care about the designer as well. Okay, so I've got my original table already saved. I might come back to that information later on, but I'm going to remove that. I'm also going to just take the best for any 1 year, and I'm also going to convert transistor count to numbers, right? So I'm just saying to myself what's going on in this case. And then I've got here the processors. I guess I'll keep that, yeah. But really the only things that I really care about is the transistor count and the date of introduction here. So I'm going to go for this one. I'm going to 1970, and this is 7 4. Oh, hang on. So what's going on there? Why is that so high? Okay, so this is kind of strange, right? So already I've got a bit of an issue here. Like I want to find a progress per year. I want it always to be beaten. So why is that worse? And then we can see that this is going up. And then I'm getting this one here. Well, why is that so much better? Okay. Well, I might keep that then. So, I mean, do I keep this? This seems like an anomalous result, to be honest. So I think even to start off, I'll probably get rid of that. It seems like there's too many conditions on this. So I'm going to start in 1971 and hope that I go up to 2020. Okay, so, right. So again, I'm going to take out the 1970 data, removed, because there's, why? Anomalously high. Spell that right? Anomaly. anomalously high. Okay, anonymous, anomalously high. Okay, so so I'm going to take that out. I mean, just I'm saying what's going on as I go. Okay, so taking this one out. Right, so let's remove that then. Let's go to 71. It's going to take some time. If you want to skip ahead on this one, you can do. I'm giving myself just an hour on this. So I'm going to go, I'm going to remove that. No, that's good. Okay. So what have I got? I've got 2250 there. Got here. It seems like there's no problem with that. So 3078. Then this one is not bigger. And the next one, which is bigger, is here. So we've got this one, and now there's a comment on this which I've missed out. So I think 35 referred to. See how confusing this can be already? So 35 referred to a little result. I might need to check these things. So seems to be okay. Seems to be okay. So I'll stick with that. What did it say on here? Okay, maybe that first one was okay, but that first one didn't enable me to. It was so high, 75,000. I wouldn't be taking any results until over 10 years later. So that's why I'm removing that. Okay, so let's. I mean, should we keep this? Strange. 7,000. I mean, maybe that first one should have been kept in and just commented on the graph. Okay, so 1970 was 7,4. I'm already having big issues with this. Okay, let's put that one back in. Okay, so 74442. This is 1970. So we'll stick with that. I'm going to take away these things here, as I said I was going to do. I'm going to delete those columns there. Just insert a column here as well. Right. Okay, so I'm going to keep a couple of these anomalies here. We've got 3,000 there. It may recognize. Yeah, actually, look, it's putting the comma back in again. That's just when I go to Control and 1. If I go to Format Cells, then if I go to Number and I go for this, potentially I don't want any decimal places. Okay, and I go to that, then it will get rid of my comma. So I don't need to get rid of my comma. Okay, that's just the formatting of the cells there. So don't worry about that. Okay, now 74. I'm not interested in anything which is any of these because I only want the best result from 1974. Okay, 75, best result. But then I want my result to be beaten, but I'm going to include these anomalous ones as well. So I want my result to be beaten. So the next time it's beaten looks like 1978. Okay, so I'm going to take that away. I mean, I could keep all of that data in fact, but I really just want to know when the record is broken each time. That's my interest. It's possible that I could keep all of this other information in. You can argue that I should. Okay. 1978 was broken again. So record was broken then. It's broken again. Let's just go back and see, right, when was the record broken again? Right, from this one, it was broken again here. So that's what I'm interested in, right? I was going to say one for each year, but changing my mind as I go. Okay, so then it's broken again there. It's broken again here in 1974 again. Okay, 75. No, 78 is the next one where we can see the record is being broken. Okay, then 78 again, then 79, 80 rather, this one. Okay, getting into the territory of the ZX81, one of the first home computers, which I remember as a child. Okay, what do we got here? So 55,000 there. Then we've got 63,000. Okay, so now we're cooking. Okay, so 190,000. Okay. When are we beaten? When do we beat that again? It's this one. When does that get beaten again? That's this one. Okay, take that away. Beaten again in 1989 when we have 1 million transistors. Okay, so 1 million. 1, 2, 3, 4, 6. There we go, to 1 million. Okay, and 89 again is beaten, and again in 90, 91, 92. Okay, 93, 93 again. Pentium Pro in 95, 5.5 million. And we're getting 10 million from Hitachi in 97. 10, 1, 2, 3, 1, 2, 3. Okay, 10 million, and then when we're exceeding 10 million next, not until 99. The Emotion engine. Okay, 13.5. Okay, then 99 again. Beaten. Okay, so records are plenty here. Next one, 2001. 191. Okay. We go, and getting rid of all of these. I'm just getting rid of all of. I've just got way too much data. I think that by just looking at when the record's broken, that will be sufficient to show the change over time. I think we're going next to the dual core Titanium 2, 2006, and that's 700, 1, 2, 3, 1, 2, 3, over a billion there. Next time we're over a billion. Oh, we're not. Not until 2008. There we go. 2008. And we're looking for 2 billion. 2010. Okay, so 1. Okay, then let's get rid of these. 227. 270. 1, 2, 3, 1, 2, 3. Not sure what that is. Let's get rid of that. Let's look at the next one. And the next 2012. So we're nearly there on this. Now, let's just delete that at the top. Okay, so we've got this one. There we go, that's good. So we're up at 5 billion here. 5 billion. Any better than 5 billion? Yeah, 5 billion beaten there, and seems like it's 5 billion, it's 10 billion there, 7 billion there. Okay, so 7 billion wins. 10 billion, and anything better than 10 billion? 18 billion in 2017. Okay, see, this is really well documented there. So 18 billion, 19 billion. Okay, so let's delete some of that. Okay, so 19 billion, and I don't know if that's beaten. 19 billion, 39 billion, there we go. 2019, brilliant. Okay, 2019, and there we go, that's the final That's the last record there. Okay. So that's 19 billion. Let's delete this. Right. Okay. Well, let's now. So we've got this data here. Now I'm going to need to get everything together here. So let's put this just on the same line. Introduction. Okay. Let's get rid of that. And then let's see if I can go to data and put in a filter for this. And let's go earliest to latest. Okay, so let's see if it recognizes the table. Sort A to Z? No, it doesn't recognize the table. Okay, then to recognize the table, then what I'm going to do is I'm going to put in a 1, 1, 2, 3 down here. Okay, just going to copy this one down to 2019. I don't really care about anything else there. Right, so I'm going to go to data. I'm going to get rid of my filter, and then I don't know what this is, number. Right. And let's call. Now it should recognize the table. Excel will recognize the table. So now if I do date of introduction, smallest to largest, there we go, we've got our table. Okay, so I now don't care about all of the other stuff there, right? So I don't care about that first column. So all of that can go, right? Don't care about that. Okay, so there we go. That's all of my information. This one I can see I didn't then sort out. And also, I'm just going to sort this column out here. And I just want to go Control 1. Go find that format cells. Formatting, conditional formatting. Data. I don't know. Format cells. Anyways, Control 1. Format maybe. Format cells. There we go. Okay. But if you go Control 1, then it will get up format cells for you, and you can then look at the number. What is it we want? We want. No, I don't want those commas there, right? It's looking messy. So there we go. So there we go. There's my table, and I can enlarge that a bit if I want. Now I can also let's just go Control 1 again, and let's look at the alignment. Let's just wrap the text, not wrap the text. Let's shrink to fit. Okay, because there's some things here which when I go and copy and paste bits of this table into somewhere else, I don't really. It's messy, isn't it? When you've got this massive sentence there. Okay, right. So that's looking good. You can see there's a couple more bits of data there which I need to sort out. And this one here, so it should get rid of the commas too. Okay, and right, so what I want to do now, so this is good. 1970 wasn't removed. 1970 and 1973 results look anomalous. How you spell it? Okay, so but I've kept them in. Kept in here for first graph. Okay, so I'm going to keep them in for the first graph. So there's some little notes down the side here, and this is just what I'm doing here is just coming up with some reflections as well. So those are some reflections which I can add into my project. Obviously, there's marks for reflections as you go. Okay, so I'm going to save this as well. I've forgotten to do that. So, and don't just save it on your computer as well. We've had an incident this year where a student has had a corrupted hard drive or something like that, and has lost their project completely, or at least handed in a pretty decent one, but couldn't make any changes because they handed it in via PDF. Right, so we should save it, and so save it somewhere else, save it on the cloud or somewhere as well, but I'm just going to put it on my desktop at the moment. So this is going to be Moore's Law. Okay. Right. Let's put the AC on. Okay, so this is my first clean, and I might want to make a first graph from this first clean as well. And I might want to start going in and copying and pasting things into into Word as well, because I might want to start making up my document now too. So now, obviously, I'm going to need an aim, a rationale, and I can come up with those things later on, really. But I might want to start putting in certain things, like, for example, I looked at Moore's law here, and what I might want to do is just put in some screenshots into my project. Okay, just to help me remind me what I'm going to be writing about as well. So there we go. This is coming from Moore's law. So I could screenshot that in there. Let's just make it smaller. I prefer it when I've got a little bit more room as well. So let's go narrow margins on this one. And normally I prefer these things as well when I can have them in front of the text and I can move them easily as well, right? Make them smaller, move them easily as well. Up to the moment, they are just, sorry, there we go. What are we talking about? Layout margins narrow. Okay. Where was I'm just going to keep it like that for the moment, but I'm just going to make it smaller. Okay, right. So we did Moore's law. I should probably just note down where I'm getting these things from as well. It's really important to keep your record to start off with as to what you're doing. Okay, and yeah, so I'm going to start putting some of this stuff in. So also from the raw data, I've got this. Now, this is not a nice table to put into my project, really, but I suppose I could, I could tidy this up a little bit here, and I could just talk around some of the issues of the data, to show that this is what's turning up to start off with. Introduction now. Okay, let's get rid of this. And so, I could add in my raw data. Let's get rid of this. I mean, I could tidy this up a little bit. It's not looking great. Okay, but what I could do as well is just say, let's copy a bit of this into my project and say, okay, this is the kind of data that I'm dealing with to start off with, and I'm going to explain that to whoever's marking this. This is what it's starting to look like to begin with. Okay, and I can put the transistor count website in there as well. Now, obviously, I'd put that later on at the end of the page or something rather in the footer, but I just want to keep it there to start off with. So now I've done the first clean of the data, and to be honest, I don't really need to give everything. I think. Let's see. Let's get rid of that. Is that looking all right? It's not fitting on one page. So potentially you could, let's see if I could just copy and paste that into Word. Maybe this is good, this original data, and that's something for me to talk around here as well. So let's just hover over and see the options that it's given me. Oh, that's all right. That's reasonable. Okay. Okay, so it looked like the best version of this was this, but it's still pretty nasty to put that entire table into the project. Now, look, if I do that, I've got a problem then. I can't rescale it later on if I want to. So, from my point of view, what I might do here is I might let's just get rid of that. So what I might do is just take a copy of half of it and half of it again. So I might, again, it's not looking good, right? I mean, I could tidy it up a little bit, right? And keep saving it. Now let's go to this. Let's just copy a little bit of this. So I might just copy it in 2 chunks. Okay, so there we go. And I might put that in my project. Now, the benefit of that is that I can then rescale it and I can write around it later on as well. So, maybe if I just put in a new line over here, let's Control Enter, just new page. And then I've got up until 91 there. So, in the next one, 91. Okay, so I'm not quite fitting everything on the page again. Okay, well, you get the idea, right? You get the idea that I would want to seek to put this in multiple parts, just because I want them as photos. And as photos, they might be. I know I'm missing a little bit there, but There we go. It's just put that there as well. But just as photos, then I can manipulate them a little bit better. I mean, I know I'm missing a bit here. Another thing you can do with tables is if you want to, right, if you want to, you can put like a dot, dot, dot here as well. So you could say like dot, 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 tab across a bit, dot, 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 tab across a bit, you know, dot, dot, dot. And then you're getting to the second half of the table. If like the whole table is kind of really boring, in fact, then why put it in there? You know, you're trying to hold someone's interest when they're reading this thing through as well. Okay, right. So likewise, what I could do there is I could collapse some rows here, right? I could say, look, I just don't care about the whole thing. Right, let's just collapse some rows. So let's just hide these ones. Okay, and let's hide some more, right? And hide some rows there. And potentially, you know, that's all I'm going to put in. Maybe I could put in insert a line afterwards or before. Whatever. Let's insert a line. Insert one afterwards. No. So you could insert a line there and put your dot dot dots in if you wanted to as well. Okay. If I want to unhide here, I could either go and pull this. I could like just make all of these the same height again, right? Right. I just Control Z that to bring it back again, or I could just highlight these and just right click and then unhide my columns again. So I'm back again. Okay, right, I'm saving again. I might want to make another table in a moment, but what I'm going to do right now is plot these things on a graph, right? So this should be super impressive. Okay, so I want to put in a table, so let's go insert, and do you know what? I think I probably want it the other way round. Just cut that and paste it in there as well. Just insert space there. Now, obviously, I can change things around, but when it comes to making the graph, but I think just it's easier if I just copy these things here. Okay, and it will automatically put the first column into the x-axis. So let's go insert, and let's go chart, and I might have to just flick through to see which one I want. So probably I want one of these. Probably what I want what it's calling a scatter graph, maybe a line graph. Let's try with a line graph. So it's giving me options when I hover over things as to what I might want, but annoyingly, I can't actually see what the graph looks like. Okay, so keep it simple. And see, I don't think I want that because it's just plotting the two graphs separately. I don't want that. I don't want a line graph in this case. What I want is a scatter graph. I want a scatter graph. There we go. That's what I want. And I want it joined up. So there's my joining up of it. And maybe I don't want, maybe I want it joined up like this or like this. I'm not sure. Because I don't really want curves between it. I want just straight lines at the moment, I think. Okay, so I think this is good. There we go, transistor count. I might want to change that. That's transistor count. Right, let's just get rid of MOS. I'm not really sure what that means. Should look into it. Transistor count, you know, label it properly, okay? What, since 1970, okay, so since 1970, and okay, and then I probably as well should have some axis titles here, but I don't have them. But if they're not on there, and if I can't figure out how to put one on, I could always come up with a text box in my project and put it by the side as well. So you should really have you should have what this is called on this axis as well. Okay, that's looking pretty good. I'm happy with that. It's kind of what I expected as well. Maybe as well, this is we call it chart one. Okay, chart one or something like that. And then you could also have reflections, which were, you know, chart one reflections. You can make that up yourself, and you could then come up with some sensible suggestions on this, right? Okay, so we've got that, and let's see if we can just copy and paste this as well. So we can copy that. Let's go for another new page, and let's paste on this one. So that's grand. There we go. We've got this thing here, so that's good. This is nice. Okay, this is looking good. I don't really want until 2030 though, so let's get rid of that. Let's how do we do that? Let's format axis, and what do I want on this one? I want it to go up to 2020. So here we go. Let's change that to 2020. And I don't want it to go from 1960 because it didn't start there. But I could. Let's go 1970. Okay, and let's go with that. Oh, look, it goes logarithmic scale here. That's nice. Could use that in a moment. Right, so that's good. Oh, and it's already changed it for me as well. So that's great. Okay, so this is good. This is something to reflect on. What I'd really like here as well is a regression line as well, though. So I wonder if we can put in a regression line here. So add trend line. Ooh, okay. So again, we think it should be exponential. That doesn't look good. Okay. Okay. Oh, it was because it's linear. I was clicking on the wrong thing. Exponential. There we go. We've got an exponential graph there. That's good. And display equation on chart. Oh, okay. Well, that's going to need to be changed. Okay, because you can't have that notation on here. But that's fantastic. And what else does it say? It says display R squared value on the chart. Right, yeah. Let's R squared is a measure of the fit. Okay. So there's R squared as well. So that's going to be good. We need to change the notation there slightly because you can't have E minus 292. Okay. Okay. That's particularly nasty as a coefficient at the front there. I mean, that's like saying next to nothing, right? 2 times 10 to the power of a minus 300. Okay. So we definitely need to think about taking this a little further and where we're going to take that. But that's the mathematics that I'm not going to get into at the moment. Okay. So that's good. I like that. I can now copy and paste that into my chart. I'm getting quite far into my Word document. I'm getting quite far already. That's pretty good. I'm under an hour still, and I found lots of stuff out. I haven't done a lot of maths actually, but so there's that, and I want to copy and paste that one as well. Let's just see if we can copy and paste that thing. So let's get rid of that. Get rid of that, yeah. In. Ooh, good. Okay, good. Now there needs to be a reflection here on this thing here. You can't have E something. It doesn't make sense in our mathematical world. So that's a problem there. Okay, and also you can see they're using E as the base number here, and there's some, again, I'm not going to get too involved in the mathematics at the moment, but there's some nice ways of changing the base. So you could change the base of an exponential. It doesn't have to be e to the power of something. It could be, if something's doubling every year, then it should be 2 to the power of x. And you can change the base, and you can do some maths in order to find that out. By the way, you could also use some differentiation here. Differentiation has a meaning. It talks about the rate of change over time as well. Now you can see at the moment that in terms of my idea that this would be tailing off, it doesn't seem to be. But then when we did look at the table here as well, when we look in that table, just go a little zoomed in on this one, then we can see that in fact, between 2015 and 2017, it didn't double twice, and so it seems to have slowed down this Moore's law towards the end. Now, here's a nice thing that we could do. So here we could insert another graph here, right? Now, I might want to copy this whole thing across, and I might want to get rid of that. Oh, I might want to get rid of that data at the start. So let's copy this one across, right? So move and copy, move to end, create a copy. Okay. So that's clean one. This is no anomalies. Okay, this is the no anomalies stuff, right? So I'm gonna get rid of my chart now. Oh, probably can still keep it. Right, let's get rid of this one. Get rid of that data, and let's get rid of this one as well. Now let's see if that changes the formula on that too. Yes, it does. Okay, it changes the formula. It might change the R squared as well. Let's look at the R squared in the first one. R squared was 0.978, and here it's 0.99. So we've significantly improved the R squared just by getting rid of those anomalies there. So that's maybe chart 2. Okay, that's something else to reflect on. Okay, transistor count, anomalies is removed. Okay, so we can call it something like that. Right, there we go. Maybe just pull that out a little. Don't like that being on a different. Okay, I can't pull that. I don't like the formatting of that. Right, okay. Right, go away. Okay, so we can do something else here as well. Let's control and paste with this chart. Can I do that? Maybe I have to make it again. Okay, so let's make it again. So let's do these two against each other again. But this time what we're going to do is insert, I'm going to do a scatter graph again. I'm going to do this again. I tell you what, I'm going to do it like that, because that's a little clearer. Okay, now what I want to do is make a logarithmic scale. Now there's a reason to do this, because in our exponential model here, right, let's just do a little bit of working out, okay? So in our exponential model, we've got y equals a e to the bx, okay, something like this. So that's our exponential model. Essentially lift the whole thing up if you want to by adding a plus c, but it does. This should cross, exponent e of x goes through 1, and it goes through 1e and so on. Okay, and this is a horizontal scale factor that's happening here as well. So I didn't want to get too involved in the mathematics, but right, what can we do here? We've got what were we looking at doing? So if we were to linearize this, what you can do is take logs of both sides here. So if you take log of y, that's going to give you log of a plus log e to the bx, which is just log is the inverse function of e to the power of something. So that's just going to take us back to bx there. So what we've got here is this is like saying mx plus c. Okay, b is just going to be a gradient, and log a is just a constant. It's not dependent on x. So essentially, this should now be a linear function. If this graph, if obviously with the e of x graph, the one which we found, that modeled e of x exponential graph, that will become a straight line when we do this. Okay, like this. Okay, because we've already found this. But if we now plot, here's the clever bit, if we now plot log of y versus x from our table, then we should be able to find a straight line graph if the exponential model is in fact the model which we should be using here. Okay, that enables us to see where the data doesn't fit the exponential model. By the way, we can kind of see that from the table as well, and we can talk about it in terms of the table too, because because we can see in the table where we're getting doubling, between years, roughly between 71 and 74. We didn't seem to. Never seems like that it's really doubling. But we should be able to see by linearizing this data where things showed the most growth and where things showed the least growth over time. So there must have been particular periods which were better than others. Okay, now I think you can do that here by, if you go to, we click on, let's try and add trend line on here, right? So if we do, what did we want to do? Right, so we wanted to linearize, I think. So exponential, I think it gave us an option to linearize it. Did it not? Was I just looking at logarithmic? Okay, no. Right. No, so I don't want to do that, right? So let's take that back. But I do want to still try and do this. Now, what I want to try and do, because this is my y value here, I want to try and plot log of y. Let's put that to the side. In fact, okay, right. Let's put this in a little here, right? So this is my y value, if you like. So now what I want to do is log, and it doesn't matter if you use ln, so log to the base e, which is the most common, I suppose, or log to base 10. Let's just say ln of transistor count, okay? Transistor, which you may have called y. So you may have already defined this to be y, which would be much easier, wouldn't it? Let's put that in as y, or in brackets y or t if you want. So this is just going to be equal to ln y. Okay, right. So what I'm going to do now is take the natural log. Yeah, it allows me to do it in Excel. Take the natural log of this number here. Okay, right. So there we go. Oh, that's exactly 8, isn't it? What's going on there? Okay, right. So I think probably that's, change that to number. So control 1, and let's go to the number of decimal places. So let's put those in, right? Let's put 2 decimal places in. We've got nothing going on there. We don't care about this line either. So let's delete this. These reflections are no longer my reflections in this case, but I can come up with some reflections, surely. Okay, and I can get rid of that line as well. I'm not sure why that was there. Oh, that's because I deleted one of the lines. Okay, so now let's just take this over to the side a little. And let's make that like that. That's good. Let's make the year. Just call this year. Okay, so year, and then hang on, year, and then call that X as well. Save this, and right. So for the next thing, my next trick, what I'm going to do is plot log of y against X. So I'm going to copy this down here, and then I'm going to press Control, and then I'm going to copy this down here as well. So Control is just allowing me to select 2 different sections. Okay, so now I want to do insert. Again, I want to do a, oh, that was kind of fun. Okay, so now I want to insert my line. Now in one place it looks like it's going down. Is there a problem with my data here? It's all going up. Oh, this one didn't go up. Right, so that shouldn't have been in my previous bit of data as well. Okay, I can see there was a mistake there. Everything else is going up. Checking through. Okay, so I had a problem there. Let's just go down to, I could have just deleted a row, of course. Right, so let's do this again. So we've got X, and let's do Control, and this. Okay, and now let's go to Insert, and let's go to Insert a Chart. And in this case, I kind of like it without the dots here. Here we go. Right. There we go. That's pretty brilliant. So what we should be getting here is a straight line. Well, this is good. Okay, so we can obviously call it something, right? But I'm not going to bother doing that right now. And you can obviously change this axis, and I'm not going to bother doing that right now as well. And you can also, here we go, you can also come up with a line of best fit here as well. So let's go add a trend line. And let's add a linear trend line in this case. And let's show what that trend line is. Give it with me. So let's display the equation and display r squared as well. Now that will be the same r squared as the other graph, although I've just deleted a bit of data there, because it's essentially finding the same relationship between the data. It's just that what I have now is I have what it will give me. Here we go. It's just what was it? 0. Let's just say 0.3, 0.4x, and 700. Take away 700. Okay, 0.4x. So what you're getting here is this. You're getting log of y equals 0.4x minus, what was it, 600, 700? Okay, minus 700. Okay, like roughly. Okay, so now m is this, and m was b. So 0.4 was in this model here. So we can then say this implies y equals b. So we've got e to the 0.4x there. And in order to find a, well, a is log c, okay? So a is this, so we've got log c equals minus 700. So if you take e of both sides there, then you're going to get c is equal to e to the minus 700. Oh, that's nicer than actually using a constant at the front, which has, times 10 to the power of minus 300. Okay, so you could use as your constant e to the minus 700 there. Right. Nice. Okay, so there's us going from the linearized version to the exponential version. Away, so that's pretty nice. And the R value should be the same in both cases there, whether it's doing an exponential model or this now log version, the log version that I've created and linearized. It should give us the same R value. Right, so that's really nice. Now, what this shows us, okay, I could write some more reflections if I wanted to on this, and I should do. But what this shows us is that, pretty much we've kept to this path throughout. We can see that just before the 2000s, we seem to be dipping below the trend line. So that would indicate that progress had slowed slightly. And then between 2000 and 2010, it seemed like progress was above the trend line. So we would notice then that we're going to get a more than doubling, or whatever the factor is, whatever the multiple is each year. It's going to be above that long-term average. And then you can see in recent years, we've been hitting that average again. But it doesn't look like it's 2 to me. Okay, so there we go. So what we'd need to say here, of course, is this is log of y as well on this axis. We need to say we've done log of the transistor count. Okay, right. Now, should we just do a little bit more mathematics here? Let's just do a little bit more on this. Okay, because what I'm interested in is what is that value? What is that multiplier value? Okay, and now I'm not seeing that multiplier value easily at the moment, but I can see, here we go, sorry. Right, I can see that roughly speaking, because I've got this as my formula here. Now, I can change this. I can say, well, that's E, I can use laws of indices here to essentially say, look, this thing here is A, instead of E to the BX, I could say that's E to the B to the power of X. So that's changing it to a slightly different model there. And this thing here is going to be our multiplier each year. For example, if I said 2 to the power of x, that would be 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. You can see that's 2, 4, 6, 8, 2, 4, 8, 16, and so on. Now, if there's a multiplier at the front, like, I don't know, times 3, then that's going to give me out the numbers. By putting in x is 1, 2, 3, 4, that will give me out, well, let's put in 0 as well to get out an easy start number. So if I put in 0, I get out 3, and then it doubles each time. So I get 6, I get 12, I get 24. That's what I'm getting from this. But the 2 is going to show us the multiplying factor each year. Okay, so in this case, all I need to do is say that e to the power of 0.4, e to the power of 0.4 is going to be my multiplier each year. I'm excited about this, as much as you can be on a Friday afternoon. So e to the power of 0.4, messing up here, just doing this on my GDC. So I've got e to the power of 0.4. Oh, that's nice. Okay, if you can see, you can't, but now you can. We're getting out the answer of 1.49, roughly. And I know I've made super simplifications in my formula here as well, but it wasn't really 0.4, was it? It was 0.35, something like that. But that's coming out as about 1.5 there. No, I have to put in e to the power of 0.35. Yeah, okay, so that's like 1.42. Okay, so anyway, I'm getting out something like 1.5 here, right? And what that means is that we have a multiplying factor each year, which is roughly which is roughly 1.5. So Moore's law is not following. A result of this investigation so far is that Moore's law is not 2, it's been 1.5, and pretty consistently over time as well. And we can see that that's only sort of veered off course a couple of times back in the sort of when it declined a little bit in the transistor count going from year to year times by 1.5 declined a little bit in the late 90s, and then it increased from the late 90s through to sort of about 2010. We can see that we are from about 2000 to 2010 we can see we're above the trend line. That would mean to say that we are multiplying by more than 1.5 in those years. Right, nice investigation, hey? That's just over an hour, I think, and we've got quite far. Okay, so top tips then. Let's just pause for a moment. Let's get a drink of water. Okay, so we should come up with some top tips here. Reflect on what we've done. Okay, so I think it's really important that you don't delay doing something about the IA. And even if you collect data to start off with, which you're not going to end up using here, you will create skills which are going to be useful for later on. So almost it's worth just trying this out, trying and collecting some data and trying to clean it up and, make sure that it's all organized. These are all really important skills. A database project, likewise with a project where you'd have multiple factors and you might be looking at correlations between those factors, is generally a fairly easy project to do, but is also not necessarily extremely exciting or is going to show that much personal engagement from the point of view of the examiner, because we know when we're marking these things that these are relatively easy projects to do. And the mathematics is it's good level mathematics, but they're quite common types of projects. However, you could be spending 6 months looking for that killer idea and not finding it. So try and think about what you might be interested in, whether it's some global data, whether it's the environment, whether it's some sporting data, whether it's something which follows a growth pattern. Try and think about the data that you can find, and then try and clean that data. And every time you're cleaning it or doing something to it, make a new sheet. So maybe what I should be doing here is doing even another sheet after that. But then this sheet is no anomalies, and what else was on this one? And linearizing. Okay. So yeah, make a start. Like a database project could be a good one and could be a solid one and could involve a lot of mathematics. Once you've got to a certain stage with this, your teacher, if you hand in something like this as a first draft, your teacher can say, okay, well, have you thought about doing this, taking it forward? Have you thought about, involving this other factor or considering what's going to happen in the future? How reliable is this for making predictions in the future? Is there some physical limit to this? You can be thinking about those extension questions, which could lead on to more mathematics. And if you're doing more research into other types of tests or transformations or whatever it is in terms of the mathematics there. But I'm an advocate for doing database projects simply because they're likely to score solidly. And a lot of the time you kind of want to get the IA out of the way and focus on spending a long time studying the course, get it out of the way, make it decent. The killer idea is hard to find. Okay, so there we go, there's that. Other things which are important is, so when you're collecting things, I keep saving things on one Excel file, keep adding new tabs at the bottom every time you're changing something or doing something to it. Keep writing down your reflections as you go. You might want to be writing down your reflections in your Word document as well. Make sure that you are saving your where you're getting this from. So you're creating your bibliography, saving all of your links so that you can reference things later on. Sometimes when it comes to Word, I personally wouldn't use the tables in Word. I would use the tables in Excel and just take pictures of them, which is what I've done, and then copy that into this. This obviously doesn't look great, but I noticed that I didn't come up with any lines around the tables. Essentially, I already think there's lines around the tables in Excel. So, that's just another time-wasting thing to do, I think. Okay. You may have some ideas on this as well. I mean, you may have some ideas that you want to write down at the start in terms of where you think things are going to go in the future. You can talk about your personal engagement here as to why you think this is important. Yeah, okay. So there we go. I think I'm going to stop there. Hopefully that was useful. Thanks for sticking around with me.